Hey, look, I'm going to talk about DC generators and motors in this video. I'm going to talk about the difference between them, how they work, and the types of them. If you're interested to watch more videos about motors, I have opened a Vax vacuum cleaner motor. You can watch those videos. Also, leave your comments below. Thank you.
To learn more about generators and motors, you can have a look at the YouTube channel at Genuine Mistake or the website quantumania.com. So, a generator receives mechanical movement as a rotational movement and it generates electricity. Now, if you have a look here, a generator receives the rotational movement and it will give us electricity or in an electrical form of energy. Whereas a motor receives electricity and it generates mechanical movement in a form of rotational movement. So if we have a motor here, then it is receiving electrical energy and is giving us mechanical energy in a rotational form. As we know from before, to generate electricity, we need a conductor, a magnetic field, and movement. Either a magnetic field or the conductor should move. Now, if we have a permanent magnet with N and S pole, we know the magnetic field direction will be from N pole to S pole. And then if the conductor is moving in between, as you see the star is showing the conductor, then what is important for us is the angle that this star or the conductor is making with the magnetic field. Why? Because when the conductor and the magnetic field are perpendicular to each other, we are making the most voltage. So if we assume that alpha is the angle between the conductor and the magnetic field, then when the star is at the pink point, the conductor and the magnetic field are making 90 degrees angle. Or in other words, alpha is 90. And if the star is at the purple point, then alpha is 0, meaning that we're not making any electricity because the magnetic field and conductor are parallel to each other. So this is one factor that is important for the amount of the voltage that we're generating in this situation. But then the next thing that is important is how big the magnetic field is, or how many of those lines of magnetic fields do we have there, which we call them B, and in the formula you can see the B. The next thing is the length of the conductor, how big our conductor is, and we show that with L in our formula. And the other thing is the velocity, how fast the conductor is moving. So that's another factor. Well, to show or to bring the factor of alpha in the formula, we need to know the sign of alpha. Because as we know, the sine of 90 is 1, and that's why at 90 degrees we will make the maximum voltage, and at 0 degrees, because the sine of 0 is 0, then we will make minimum voltage or 0 voltage. Now we can show all these factors in a graph with horizontal axis as the angle that the conductor is making with magnetic field, and the vertical axis is the voltage that we're making. Now, if we're starting from the purple point where the conductor is making 0 degrees with the magnetic field, we are at 0 degrees on the sinusoidal wave. And then the star will go up all the way to get to the pink point where we're making the maximum voltage at 90 degrees. Now, if you have a look at our sinusoidal graph, you will see that it started at 0 and is going all the way up to 90 degrees. And then the conductor will go all the way to 180 degrees, where again is parallel to the magnetic field, then we're not making any voltage, and the voltage on the graph is 0. And then it'll rotate and go to 270 degrees from where it started. And at 270 degrees, we are making the most or the maximum voltage. The only difference is that the voltage is in a opposite direction from the 90 degrees. And then it goes all the way back to where it started, which now is 360 degrees. And we're not making any voltage at that point. So as you see, we traveled one full cycle. So this is called one cycle. Now, how many cycles per second the conductor is traveling is the frequency of the electricity that we're generating. And it's depending on the country is different. Some countries have 50 hertz and some countries have 60 hertz, which means that this conductor is making 50 cycles per second or 60 cycles per second. As you see here, these are the permanent magnets, and then we have the part that is the conductor in the middle, and it's moving around, which will bring the rotational movement. Now, based on that, which means that one part is moving and one part is not moving, we have two parts in a motor or generators. The part that is not moving is called stator or stationary part, and the part that is moving is called rotor. Now, if you have a look, you can see that that rotational movement in a motor or generator is making all the sinusoidal wave that we just talked about. The only thing is that in our example, we are talking about a simple conductor. But as you saw in the actual motor, we're using a lot of coils. So the formula will be a little bit different. So all the factors that we talked about are going to be in this formula too, but in a different way. For example, delta phi over delta t, which is the rate of the change of magnetic flux over the time, which if we have a closer look at it, it is bringing the velocity in the formula, but in its own form. So as we know, delta phi here is the change of the phi. What is phi? Phi is the magnetic flux. The magnetic flux are all the bars of the magnetic field that we have. And delta t is the change in time. So delta phi over delta t is bringing the change of the magnetic flux over the time. Also, we have the n, which is the number of the turns of the coil. And as we know, the coil is our conductor because it's a copper coil, right? So the number of the turns of a coil is kind of bringing the length of the conductor into the formula. So if you want to find out what is the generated voltage in a coil, then we should times the number of the turns by delta phi over delta t. Now, a generator is a little bit different since we have more coils and more poles in a generator. If you want to calculate the voltage generated in a generator, then we need to times the number of the poles, P, by phi, the magnetic flux, by N, the number of the turns, by Z, the number of effective armature conductor, and divide them all by 60A. And A is the number of parallel paths in the generator. As we talked about it before, the generator and the motor are really similar in structure, but we know that generator is generating electricity, so we're calculating the voltage generated, whereas in a motor, we're generating mechanical movement. So in a mechanical movement, what is important for us is the torque. So we have to calculate the torque. Now, how do we calculate the torque, and what is torque? I'm sure all of you are familiar with force, but force is being defined in a linear movement. But when we are talking about rotational movement, then we want to know the force in a rotational movement. So we times the F by R, and then we will define it as torque. So in other words, torque is the force in a rotational movement. Now, how do we calculate the torque? To calculate the torque in a motor, we times the B, magnetic field strength, by L, the length of the conductor, by I, the total armature current, by Z, which is the number of effective armature conductor we know from the generator, by R, which is the radius, and dividing it by A, which is all the parallel path. So we can find the torque in a motor. Depending on how a magnetic field is being provided for a generator or a motor, we are having two types of generators and motors. I'm just talking about generators, but you can apply all these to motors as well. So, if the magnetic field is being brought to the generator by a permanent magnet, then it's called a permanent magnet generator. Easy, huh? And if electromagnet is bringing the magnetic field into a generator, then it's called electromagnet generator. Now, depending on how the stationary part and the rotor part or the armature are connecting together in a electromagnet generator, we will have different types of generator. But that's a topic for the next video. So we learned how a generator generates alternative waveform. But in the beginning of the video, I said that DC motors and generators. So how do we convert AC to DC is a topic for the next video.